Singer with us here today. So Yaron is the co-founder and CEO of Robust Intelligence, but in his previous life, he used to be a faculty at Harvard University. And the way I knew Yaron that he did foundational works in algorithms, optimizations, game theory, machine learning, and so on. And it's really exciting to see what he has built at Robust Intelligence. And we just learned the news that it has been acquired by Cisco. So congratulations. We're very excited to have you here. Welcome.
Thanks, everyone. Well, thanks everyone for being here, and yeah, and thanks. It's an honor to be here. I love I love coming here, and when I was in Boston, I was always kind of hoping to get invited to to come visit here, but I never didn't get a chance. But yeah, I love being here. Like, love the kind of like everything has been like all the amazing work that's been going on here in machine learning, foundations of machine learning. So it's really awesome. So great pleasure to be here, and hope I get kind of a chance to chat to everybody and kind of like learn about the latest and greatest. And also kind of like honored to be speaking after Jan. So when I actually joined Berkeley as a grad student, I like kind of my dream was to work with Jan. He's like done like all this foundational work. And but I soon realized I wasn't good enough to be to be like an actual member in the rad lab. So so I just went with theory. So yeah, but hopefully I'm making up for it now. Maybe just a little bit about, okay, so I'll start just telling you just a little bit about, the company and kind of, this is kind of like a template, kind of like introductory slide that we usually use. Now we added this other bullet point. The story is that, we're a company called Robust Intelligence. Our mission is to secure the AI transformation. I'll talk about what that means. And then, the big news is that last week, Cisco, we signed an agreement with Cisco, which means that Cisco is intending to acquire Robust Intelligence. I didn't know what that means up until not so long ago. What it means is that there's some like kind of like logistical things that we need to kind of like get through right now, and then hopefully in a few weeks we'll transition to become Robust Intelligence will transition to become part of Cisco. Company's been kind of awarded and recognized and kind of like in multiple ways, but most importantly, it's been kind of trusted by really great companies as customers. So that's been kind of a fun journey that I'll talk about. And we raised money and had investors, and now kind of like we're able to also kind of pay some of that. So when I kind of when I was thinking about doing this this presentation, I was talking to Amin, who's working with us at Robust Intelligence, and Amin has been working on all this sort of like adversarial kind of things and algorithmic red teaming. And I thought, hey, I'm going to talk about algorithmic red teaming. He said, yes, that's a great idea. And then I said, okay, so can you also help make slides? He said, well, what people really want to hear about is the founding story. So maybe spend more time talking about that. So I decided to talk more about founding story, but also talk to you a little bit about algorithmic red teaming. Just a little bit about like kind of how we started as a company. So as Marna said, I was actually a theorist. I think I am still, or maybe I was a theorist, and I was really interested in basically understanding kind of like limitations of optimizations from predictions. And specifically what I was really interested in is this sort of like, phenomena where a lot of what we do in algorithms, basically, when we're looking at the textbook, there's a graph, and that graph maybe has weights, and then we're kind of like doing some sort of, then we're developing an algorithm that takes that, graph with weights, and then we do something, with that, with that graph, right? But actually, in reality, what happens is that there's no like kind of, you never see the graph with weights. That's never, you never really have the ground truth. Instead, what you have is you basically have like some sort of model, and that model comes from has been learned. So there's kind of like some machine learning magic that happens behind it, and then you kind of construct some sort of graph, and it has weights, but these weights you actually learned from data. And what that means is it means that actually, that can really kind of throw you off when you're developing algorithms on, on kind of constructs that are learned from data rather than kind of like ground truth, right? And that kind of, for someone who's like, for me, who's like been developing algorithms, that create kind of like some sort of like existential crisis, right? Because like, what does it mean that we're like improving something by an epsilon or 2 epsilon, approximation, right? If like this entire, data, kind of like that we're working on just like is just, just a little bit far off from, from reality, and that can like really throw off algorithms. So that's kind of what I've been up to, kind of like at my time at Harvard. So basically kind of studying, what are the kind of limitations of optimization or decision making that come from data? What are the kind of like limitations of developing algorithms with noise? What sort of noise can we, can we deal with? What sort of noise can we not deal with? So those are the types of things that have been occupying my study. And then kind of from, from more theoretical work, kind of, I kind of got some grad students to kind of like, work a little bit more on things that are a little bit more applicable. So you can see that because everything here is, I think, in the NORPS format. So that should tell you that it's more applicable. So I don't know if that, but so we started kind of like looking into actually how do we develop algorithms, like kind of for robust machine learning. And then from there, we got some DARPA grants. So I actually found this somewhere in my mailbox. So we got some DARPA grants for, developing deep learning architectures from robust classification under adversarial noise. And that was kind of very interesting and a lot of fun. And then at some point, just felt like, rather than, going for like the next DARPA grant or the next DARPA project, it may actually be a better idea to seek funding from from investors and and kind of like and do this as a as a company. I think kind of like largely because some of it is just like it's easier, I think, to get money from investors than the NSF or DARPA, which is unfortunate. And I realize I'm saying this at this like NSF Encore event. Hint hint. But then also, I think like something that's nice about starting a company is that the proof is in the pudding, right? So you can if your idea works, then people or your framework works, then you don't. It's not about getting the paper accepted or rejected. You actually see companies kind of adopting a framework that you built, which I think is like really exciting, and that's something that I think that you're better off probably doing as a company rather than kind of like an academic project. So we taught some courses on robust machine learning, and then Koji and I, who was a student at Harvard, we started Robust Intelligence. So somebody took a picture here. So what happened is, this is like in 2020, summer of 2020. It was COVID. We flew to SF. It was like kind of everything was empty. We got this warehouse in the San Francisco Dogpatch area, which is now like kind of really cool. Back then it wasn't. But we got it for like kind of dirt cheap because like COVID was happening and people were like kind of really worried. And there were maybe like kind of 4 or 5 desks, but it looks big. But it's a kind of, so we it's kind of an empty warehouse that we work from. And then, slowly but surely, we kind of started to build a company. So yeah, there's kind of like a lot of, so when we started, basically, this is literally from our pitch deck. I think this is from, from the seed or the Series A. So, we're not really kind of like business people. So, we just sort of presented axioms to investors. We said, okay, so we believe that AI will continue to grow and be adopted at an exponential rate for the next 20 years. That's axiom number 1. Then axiom number 2 is like, with everything that we know about how vulnerable, ML is, we don't think that there's any way that AI can continue on, growing and being deployed without defense and protection, right? So with those 2 axioms, the corollary is that securing AI is going to be a multi-billion-dollar market, with no limit in sight, right? So that was kind of like, first principle thinking. You know, and then I don't know where these graphs came from, but somebody found these graphs. Everything looks like it's going up. So that's good. And then we managed to get kind of some seed funding and Series A funding and all that jazz. So yeah, and then so what did we do? So we started with so it's kind of like a very kind of like abstract problem. So we're starting to think kind of like where does this matter? Where is this sort of like kind of vulnerabilities? Where are they going to matter to you know, to people, and what are the kind of like, you know, the companies or the organizations that would care? So what we did is like we started doing kind of things on back then it was on you know, on adversarial attacks. So sorry. This is so we did is like we started off with check processing. So what we did here is so let me explain. What we did is we actually bought licenses for check processing systems that banks used, and then we attacked these check processing systems. Okay, so how did we do that? What we did is we you know, so we take a check, somebody takes a photo of it, and that's the app that banks use. And then what we would do is we would manipulate the image of the check, right? So that it basically so right now it's like, you know, you process the check, it gets classified as $401. And then what we did is we actually we took the software. This is the software that banks use for check processing, and then we basically created an adversarial attack. These are like kind of so where we get the check classified rather than $401, in this case, as $701. If that makes sense. And that's kind of like how that's kind of like an adversarial attack that we use, right? To kind of like that we thought would be interesting for, you know, for companies. Okay, so and then how do we do that? It's actually an interesting algorithmic problem because checks are black and white, so you don't have a gradient, right? So you have to, if you want to attack the image, you have to basically do a combinatorial optimization attack. And then another challenge that you have with checks is like you have to get the basically the numbers to match the characters, and that's so kind of like getting all those things together is actually a pretty interesting intellectual problem. So anyway, we did that. And you know, with the original, and then you know, we attacking it is basically we put like kind of pixels on it, and yeah, that's kind of like how you create like an attacked image, and that gets classified as you know, so you do kind of like this commercial optimization search. It's a, you know, it's an NP-hard problem, and you just sort of like kind of just find like basically pixels that basically push the classification, right, of the model towards where you want it to go. So we did that, and actually interestingly, we sent that paper to iClear, and we wrote a paper which took 3 weeks. We sent it to iClear, and then it actually got rejected by the ethical committee. Okay, so I think we're kind of like we're the honorary members of the first paper at iClear to actually get rejected by the ethics committee. Okay, so if you can find it online, and you can actually find the reviews, and you can find you know the reviews want to accept, and they can actually see the the rejection by the ethics committee, which I think is like such an honorary, like who cares about getting a paper accepted? Like getting your being kind of the honorary members of getting the first paper rejected by the ethics committee, I think is like the biggest reward that anybody could ever have. So at some point, I'll update LinkedIn and I'll put that on my LinkedIn. But yeah, that was so that was like a lot of fun. And then we also did the same kind of thing for Amazon system for fraud detection. So this is again back in 2020. Amazon has a kind of a platform called SageMaker. You can use like kind of these algorithms that they have for machine learning. They have a fraud detection system. So here again, it's kind of like a combinatorial. So basically, you send in a payload, and then it's classified as fraud or non-fraud. And then what we do here is we sort of make subtle changes in the payload. We change the operating system, and we change like another parameter, and then it goes from like classifying it as from fraud to non-fraud. right? Um, so yeah, and that's kind of what it looks like. So what we did is we basically, we had these examples, right, where, you know, financial institutions would care about them, like check processing and things like that. And you know, we basically started a conversation. And at first kind of like, you know, we got rejected from kind of from everywhere, but, you know, slowly but surely, we ended up kind of like earning people's trust and developing the relationships. And you know, we actually kind of succeeded in securing kind of very meaningful relationships and having these banks as customers, which is you know, which is not an easy thing to do. So, but yeah, so that's kind of that's a little bit about, you know, kind of the story. So our perspective is that AI security is actually an AI problem. You know, from, you know, kind of different from traditional security. The hypothesis is that AI models are just extremely brittle. Modern systems that rely on AI models are prone to these AI vulnerabilities, you know, and protecting a system that relies on AI actually requires solving an AI problem. So the idea being is that, like, fundamentally, like, what we're doing in the company today is not that different from what we did 4 years ago, in the sense that, like, really what we do is we do kind of adversarial attacks on models, and whether those are image models or, check processing systems, or, these fraud detection systems, or, LLMs, fundamentally, we're basically kind of like doing the same kind of things, where we're developing algorithms that succeed in basically pushing models beyond the decision boundaries. Okay. So yeah, the kind of like to solve an AI problem, we assembled, really a world-class team of people. Obviously most with kind of like, rich industry experience. Some are kind of friends from grad school, like Blaine, who wrote the first book on adversarial machine learning. He was also with us at Berkeley. We recruited Amin from Yale, and just a bunch of like kind of really great people to build the company. So yeah, so that's kind of a little bit about the funding story. So with that, maybe I'll kind of like give some practical examples for what AI risk looks like, and then I'll go into talking a little bit more about red teaming and kind of like red teaming LLMs, which is kind of what we're doing more recently. Okay, so when we're thinking about, an AI system, if we're thinking about something that is, even as simple as what we call a RAG application. So on the surface level, we have a user, and that basically asks a query. That query gets routed to like a vector database, and basically goes to some sort of model that then responds, back to the user. But even in something that is sort of like, kind of as simple as a RAG application, there are actually a lot of, there's sort of like a lot of things that are happening behind the scenes. So for example, the vector database is taking data from, from some sort of application. The production ready model is based on a trained model, which takes public data and has like maybe it relies on an open source model. And there are basically kind of like all these different risks in that model development life cycle. Okay? So one example that I want to talk about is, I'll start with like kind of talking about model theft. Okay, this is sort of more classical security. So when we have an open source model, like on Hugging Face, actually, what happens is the way that models are stored on Hugging Face, they're stored as they're stored in kind of pickle format, or formats that are similar to pickles, right? And the reason is because models are just like very, very large, right? And basically they need this sort of deserialization. The issue is that when they're stored in this format, when you're downloading these models, they can basically have they basically can perform arbitrary they can do arbitrary execution of code. So specifically here, we planted, models on Hugging Face, and then, you download them. And then what happens is when you download them, we do this kind of like data exfiltration, right? So we basically take some, like kind of data from someone's laptop and we send it somewhere else. Okay? So this is what it looks like. So they're actually kind of like robust intelligence, Easter eggs, kind of like in several places on Hugging Face. But also beyond robust intelligence, we scanned all of Hugging Face and we actually found like thousands of models that have, various like malware, adware, just a lot of executable code, all these things that just should not be there. Okay, so just generally kind of like one of the big fears that that organizations have, that security leaders have in organizations, is that they have thousands of developers that are accessing Hugging Face, right? And across all of, Hugging Face, there are all these sort of like, potential for, for this kind of like model backdoor, right? So it's like huge security vulnerability. So that's something that, CISOs at organizations care very much about. And, in a lot of cases, they actually shut down Hugging Face just completely, until kind of like sorting out this issue. So this is actually, it's a more of a classical security problem rather than an algorithmic security problem. But this is, but it's a great entry point or great kind of conversation starter with, with security leaders at large enterprises. One that like kind of we care more about is things that happen in indirect prompt injection. And this is where basically, you can kind of like feed in all these different instructions into the large language model in various ways, shapes, and form that basically get the large language model to perform, these sort of like tasks that it's not supposed to. So I'll give an example. So here's like what we did is we developed just a classic, RAG Q&A kind of application. And what it does is it basically just, this application just uploads data from, various sources. And then if you kind of query it, ask it for some information, it can give you the answer, and that's fine. But there are some questions that you would ask, and what it does is it gives you this answer. And this answer is like this sort of, image of a scary JPEG. And what it does is basically it does actually data exfiltration. So it takes data from the LLM and then it sends it to it just uploads it to Wikimedia. Okay, so this is a huge kind of risk that organizations are facing. And the way that this is doing it is what we're doing is when we're uploading documents, what we're doing is we're basically hiding instructions for LLMs in white text in the PDF of the document. Okay, so you're developing a RAG application. RAG application takes data from the outside world, or even within your own organization. And then what you can do is you can basically just put these different PDFs that have this text that's hidden in them. And what this text is, it's instructions to an LLM, on doing kind of various things that an LLM is not supposed to. In this case, it's instructing the LLM to, do data exfiltration and then uploading data to some source. Okay, so this is again, kind of like a very big vulnerability that organizations have. One of the things we did is we, if you guys know, ever use Pinecone. So Robust Intelligence is basically security provider for Pinecone to actually do scanning of vector databases to block these kinds of attacks. And then the final one that I'll just kind of mention here is kind of this misalignment with fine-tuning. So this is actually an example that we saw with one of our customers. So what happened is that basically fine-tuning LLMs breaks model guardrails. So when you're using kind of like a llama, llama model or what have you, these models have these internal guardrails built into them that we'll talk about in just a bit that are supposed to prevent the models from doing or saying kind of bad things, right? What happened is that this is like now, I don't know, like 8 or 9 months ago. This is by the way, this is a huge this is a Fortune 100 company that deals with very sensitive data. What happens is that they sort of trained this llama, I think it was like a llama 2B model, and they took the model and then they fine-tuned it, right? They didn't do anything adversarial. They just sort of fine-tuned it on their on their specific data because they wanted to be more effective. But actually, what happened was that as they did that, it actually broke the internal guardrails of the model. So you would then sort of, if you would then kind of query that model with like very naive queries, very simple queries, it would just give you like kind of horrible racist responses and kind of like do all these things that it's just not supposed to do. So it just kind of like broke the internal guardrails of the model. And then we kind of experimented with that, and we saw that it is actually the case. It's not only that one customer, but you actually see that on the original Llama 2.7b model, I guess kind of like in this test, there were like kind of, I don't know, 80 alerts, and the fine-tuned version, the number of alerts grew to 144, right? This is kind of from our own kind of tooling. And then we started seeing that happen kind of like for more and more customers. So now kind of when you're inside these organizations, this becomes like a massive problem, right? You have, again, you have like kind of these data science and, and machine learning teams that are fine-tuning models. And now every time that that they're fine-tuning these models, you're kind of thinking in the back of your head, there's a good chance that their fine-tuning is going to break the guardrails of the models. And I'm going to expose a chatbot, and I'm going to expose some sort of tool, right? That is, that is now kind of like, I don't have any filters or any guardrails on that tool. So that becomes like a huge problem as well. So what do we do? Basically, when you're thinking about like an enterprise AI workflow, you can think about it all the way from like source to development to production. So in the sourcing phase, you use like Hugging Face, and then in the development phase, you use like kind of a Pinecone or an NVIDIA for your vector database, and then you develop on Databricks or MLflow, and then you productionize everything on AWS or Azure or what have you. So basically, what robust intelligence does is it connects to these, it connects to this workflow, and it just basically goes through kind of like all the steps automatically. So it looks at if you're using kind of like Hugging Face models or anything like that, we just do a kind of code scanning. That's something that's pretty not hard to do. But then kind of after code scanning, when you're actually uploading models, we automatically test these models, okay? And I'll talk about that in a minute, but basically we take the endpoint of the model, we run, basically we send in like thousands of prompts to these endpoints, and then we evaluate the response to sort of see if there are any risks in those models. And then finally in the production phase, we basically take these models and we protect them with this AI firewall that is kind of like guardrails, right, for these model endpoints, right? And what these guardrails are, they're basically a series of kind of like models that we develop internally that are developed to prevent jailbreaks and kind of like all these sort of bad things that you can that you could be exposed to when you're releasing models. Okay. So that's kind of so that's what we do. So the idea is basically an enterprise, an organization that uses robust intelligence can kind of like automatically protect itself from kind of like these AI risks that it has, right? So that's kind of that's the point. Yeah. So with that, I kind of this is the part that I that I asked Amin to kind of come into, and this is where I thought I'd talk a little bit about kind of one part of what we do, which is around model safety and algorithmic red teaming. I thought I would focus on that because it's like it involves a little bit more research than some of these anyway, some of these other things. But maybe I should pause to see if there are any questions because I've been talking for like a long time.
The industry gave for the checks with the pixel thing.
Yep.
To actually, for it to be a problem,
yes,
you have to like intervene within the app.
Yeah.
Put in your pixels in. How did you do that?
Yeah. So we actually also hacked. So one thing I didn't say is we also hacked into the app itself, so that you can upload, kind of like change the images that you're uploading. So yeah, so people could yeah, could kind of, this is a good way to make money, I guess. And
Yeah. The other thing is that even without AI, you can just like I can just print a check.
Yes.
From you,
Yes.
And upload it and like deposit it in chains. So this was already a problem.
Yes.
This is not an
Yes, that's true. I mean, first of all, let's acknowledge that, that we're not, that our business is not based on check processing, right? But okay. Now with that said, I'll answer it to you. I'm digging into like kind of my answers from 4 years ago. Well, true, except that like legally, like kind of when you did that, you actually actively forged the check, right? Versus this being kind of a mistake by the AI system, right? And therefore you're not accountable or responsible to it, but it's actually the check processing system. And that's actually when well, I'll also say that like we kind of happily presented this to check processing systems who threatened us like with a lawsuit. So they weren't too happy about that. Yeah. Yeah.
How do the companies actually like interface with the product? How do you make sure that integration?
Well, that's a great question. So yeah, I mean, so without kind of like, going too much into the details, yeah, there, for basically, there, we integrate with like, with model repositories and, all these sort of various things, we just kind of like we take kind of like model endpoints. So sort of like the integration is the integration is not a big lift in theory, but in practice, like integration can be can also be tough. So there's like one customer that we're now kind of like on, I think day 120 something of kind of like deployment. This is a kind of particular customer that has kind of like a very difficult requirements and things like that. So in theory, kind of like there's a world of SaaS where if you're kind of like if you're happy to use SaaS products and everything is like very immediate. But the reality is that like candidly, the enterprises right now that care about AI risk are also the ones that are in regulated industries, and then those ones are they're more cautious about using kind of like SaaS products from a startup. So there's sort of like there's sort of like a bigger bigger deployment requirements. Yeah. Yeah. So great question. Yeah. So we so as a company we do like we do various things. But number one is we have our own research, and with our own research it forces us to I think we're maybe we'll see in just a bit, like we're ahead of the curve in many ways. And then that also forces us to kind of like understand the state of the art and make sure that we're kind of protected against it. And then separately, we have like another team that does threat intelligence research. So they have like actual systems that like kind of listen to everything that's happening on the web, also the dark web. And then basically they kind of test some of these things, and then they and for the things that are attacks that are successful or kind of real risks, they bring that into the product. So yeah, there are kind of like various things that the company does. Okay, good questions. Okay, with that in mind, I'll talk a little bit about kind of algorithmic red teaming. So kind of like when building models or LLMs, people have kind of basic safety protocols, and which we kind of like largely call model alignment, right? So the simplest one is basically kind of collecting data and training kind of like a supervised policy. And then beyond that, there's you can kind of like collect data, compare and then basically train a reward model, like kind of a, with reinforcement learning. And then kind of more interestingly is you can kind of like optimize a policy against that kind of like a reward model. So those are all kind of things that people do for, just doing basic kind of model alignment. The challenge with model alignment is that number one, it requires a lot of human effort, right? And also kind of like, which, not only does it require a lot of humans, but also, it kind of like, subjects humans to a lot of like nasty data and kind of like that people don't, is just kind of taking a toll on people. And the other thing is that it's not really effective against adversarial attacks, right? So it's good for kind of like, seeing benign data, but not the kind of the corner cases that attackers actually use for basically getting models to do things they're not supposed to. So one of the things we do in the company is we actively, we do a lot of red teaming. You can ignore the papers on the left. That's just, but really kind of like, so all these things are like kind of things that got published in I think the last year, things that we've done, kind of like things that got published in the media about, various things that we've done on kind of like red teaming. Like one, like we attacked like NVIDIA's guardrail models and that got picked up, or, we attacked, ChatGPT and we like kind of, we showed how to do very effective data poisoning in the wild and things like that. So one of these kind of like, these things to kind of like with red teaming is it's it's something that experts could do. It's like something that, if you have people who are very skilled and understand kind of like AI systems, they can kind of like, build an algorithm or kind of like build kind of like these methods around it. But something that I think is just kind of like much more, effective that we wanted to create in the company is this idea of algorithmic red teaming. And this idea of algorithmic red teaming is basically the ability to basically generate algorithms that automatically succeed in jailbreaking models, basically in getting models to do things that they're not supposed to. But we wanted to basically be able to do that algorithmically. So we created this method called TAP, and that got picked up by various sources, but this is but this image I think is from Wired. Okay. So what is jailbreaking? Basically, jailbreaking an LLM means that we were generating prompts that circumvent the LLM guardrails. Okay. The easiest way to kind of like understand that or see that is basically through basically getting the LLM to sort of say things that it's not supposed to. So here, like if you give it a prompt that directly asks an LLM to develop a strategy for hacking into a government database, the LLM says, sorry, I can't do that. But if you kind of craft that that prompt in a sophisticated way, right, then the LLM will respond to you and now give you ways of hacking into kind of a government organization. So this is kind of like the easiest way to kind of like see this. But the reason that I think that jailbreaking is so important is not so that we can learn how to hack into like a government database. It's basically, this is a way of getting LLMs to do other things, and we'll show kind of some of these other things that I think are really important, right? But you saw some of them, you saw hints of some of them. You saw kind of data exfiltration, posting on kind of on websites, things like that, and those are actions that are much more, I think, much scarier. Okay. So we wrote this paper. I don't know how I got to be an author, but maybe because I'm CEO of the company. But really, this was led by Amin Karbasi, who at the time was at Yale and in Google, and since joined us. And so this is a method called TAP, which stands for Tree of Attacks with Pruning. And it's it's just like a really great method. And I'll tell you kind of like how we use it in the company in just a bit. But the nice thing about this is that it works kind of in a black box fashion. So we just need kind of black box access to an LLM. It generates prompts that are meaningful English text, right? So it's not sort of, doesn't use all this kind of weird things. It's like it's kind of, these are actually prompts that people can actually put in, and it's completely automated. So it means that it's algorithmic, it's automated. We basically, I can tell you, we use this for, one of our customers is Apple. And if you saw like kind of the Apple Intelligence release, so Apple came to us with like a list of 23 risk categories and subcategories and 300 kind of categories of risk that they're interested in. And we just aim tap at those categories and just generated a bunch of attacks. And then Apple used that for further release with Apple Intelligence to safeguard the models. So that was kind of like one of the kind of rewarding moments of this. By the way, I'm happy to say that this, we send this as a paper. It got rejected, from ICML. I'm hoping that I'll get into in Europe, or I forget which one. It got rejected from one. I forget, I don't know which time of the year we're in exactly, because the weather is always the same in California. But anyway, we got rejected from one, and now we're submitting to another, and whatever. But yeah, so I think it's as I said, the proof is in the pudding, right? So anyway, so what is TAP? Very briefly. So it involves 3 LLMs: the target LLM that you're attacking, an attacker LLM they're using to basically generate kind of the prompts, and then the evaluator LLM, which is kind of the interesting bit. What the attacker does is it uses a tree of thought method, if you guys are familiar with that. So basically kind of like creates a kind of like a tree of kind of like a reasoning to like help the LLM to kind of like reach the right conclusion. And it kind of like continues on refining it until the target LLM is broken. And then what we're using is every time, to avoid kind of like this exponential, kind of potentially exponential like increase, what we're doing is we're using an evaluator to basically decide on which parts of the tree should be pruned out, should be cut out, right? So that we can kind of like effectively create kind of small trees. And Amin is an information theorist. So there's some sort of information theory, like kind of, reason or, way that the evaluator works, but I don't know what that is, right? But it's supposed to be like very, very cool, okay? So yeah, so it kind of look, if you kind of like, if you tracked it, it would kind of look like this. It basically kind of like starts kind of branching, and then the attacker has kind of basically different hypotheses, and then the evaluator prunes like kind of the one on the left out and leaves this branch in, right, and then kind of continues with the branches as long as the evaluator believes that this prompt has a chance of succeeding in jailbreaking. And then when you're kind of like looking at how well it does, so you basically look at the average number of queries that it takes to jailbreak any one of these models here on the right. You can compare it to like another method that came out, I think, at the same time, which is called pair. So also black box access, and then I think there's another method that uses wide box access, and TAP does really well on all models but Llama 7B. I'll talk about that in a bit. It uses, average number of queries is very, very small. It's like 22.5, queries to jailbreak, kind of jailbreak a model. So it means that it's very cheap for us to break models. Which is great. And that's kind of how we can apply it to like kind of generate like millions of prompts immediately. You can look at, has like a nice success rate across like different categories of risk. These are the categories we use for the paper. But like I told you, like kind of, for Apple, we use like 300 categories. I'm probably not allowed to say that way. This is what we have for Apple, but anyway, I hope that we're all friends here. And then when it comes to human judgments, it also does really well against like open source models and closed source models. And it also has like nice transferability results. So basically, the prompts that you use to jailbreak like ChatGPT-4 have 79% success rate at on Vicuna, for example, right? On Llama 7B, it has 0 success rate, but then on the other ones, it transfers like pretty nicely. So it has this kind of like nice transferability results. Yeah, and then just kind of like the last thing I'll say is that we've been fortunate to work with Madi, who's a Hammond student, this summer, who came in and actually, you guys can see that like on Llama 7B, it's like 0. So if you catch Monty during the break, he can tell you about this like awesome new method that he developed using bandits, like in, kind of like a kind of best arm selection, on actually getting basically kind of like solving the hard problems, like kind of all like how to basically get actually attack Llama 7B and then basically just like really kind of like make this method just really, really powerful. So yeah, so I think it's really cool, and I'm also happy that people like to see us using kind of best arm selection. That's a story for another time, but yeah, it's really, really cool. So last thing I'll talk about like here is like this kind of is data exfiltration. I know we're like at time. I know this is lunch, so I'm not going to show you the slides. I'll just tell you like what it is. Okay. So basically, we talked about like jailbreaking. You can get models to sort of say things that they're not supposed to say. The cool thing is that you can actually do with jailbreaking. This is like with another intern that we had this summer. This is Ellen. She's now going to like start her grad school at NYU. What you can actually do is you can actually extract training data from models, right? So what we did here is, as many or some of you may know, there's the New York Times is suing OpenAI for basically using its copyrighted material in training its models. And what you can actually do is you can actually kind of show evidence of that, using these methods. How? So basically, what Ellen and team are doing is basically they're showing how you basically feed in parts of kind of like New York Times articles, and then you get the LLM to kind of give you kind of more and more parts of the article, so you can then compose an entire article. And you can do that not only with articles, but you can do that with training data. So basically, what you can now do with these sort of jailbreak methods is you can actually, just by black box access, you can start extracting, training data that the model is trained on. In, New York Times case, it's like copyrighted material. In other cases, it's like, training data that's supposed to be sensitive, which is, huge issue. This is like kind of the #1 nightmare of all these organizations. So we, yeah, so we think this is a meaningful one. Okay. So yeah, so I know we're at right at lunch. So I'll just yeah, I think I'll just kind of wrap up with that, and happy to stick around for any more questions that people may have.
Wow. So not that it was whole, it's just based on this effect, right?
Yeah, that's a great question. Well, of course we don't know, right? We hypothesize, but I think that like our hypothesis is that like Meta and building Llama, have put in an additional layer of kind of safety, and that additional layer of safety that's embedded in the model is is just has proven to be kind of more effective against against these methods. So we think basically the simple answer is that I think they put like better safety mechanisms, but Monty like managed to break through those. So it's just sort of it's limited in how good those can be.
Have you tried to deploy safety compatibility technique?
Not that I'm aware of. Thanks, everyone.